Let's take a look at solving systems of equations with two variables. So in systems of equations, right, if we're dealing with a two-variable system, we're going to need two equations that deal with those two variables to create a system. Now, whether we can solve that system or not depends on whether it's consistent or inconsistent. So a consistent system means it has a solution, which means the two equations graphically have an intersection. They're going to intersect each other. And that's what we're looking for, those intersection points. So that's a way to check our systems, is to solve them, of course, graphically. But with our systems in this section, we're dealing with systems of two variables with two linear equations. So we're going to look at systems of linear equations. Now, three methods, we'll, of course, look at it graphically. And then we'll go over a couple of algebraic methods. We're going to look at the substitution method and the elimination method. And you can pick any method you like as far as solving it algebraically. You have two choices, substitution or elimination, and then a good check step would be graphically. Now let's start off with graphing. So again, if we have a system of two equations with two variables, if we want to graph it, the first thing we're going to do is put in graphing form, and that's right, solving the equation for y, right, which in a linear equation would be putting it in what, slope-intercept form. And then graph the equations, and when we have graphed them, we're going to have one of three scenarios. We're going to have either the two lines intersecting at one point, which means we have one solution. That solution is that intersection point, that ordered pair. And that's what we call a consistent system with independent equations. The equations are independent of each other. They're not dependent. There's only one common point. There's infinite points that have nothing to do with the other line. So they're independent equations. Now we could also graph two lines. Instead of intersecting at one point, they could intersect at every ordered pair, every point xy, which would be the same graphs, which would mean we have infinite solutions. We have infinite intersection points. So there's infinite ordered pairs, say x and y, as those are our two variables in our system, that satisfy the two equations. So that would be a consistent system, definitely has a solution, is consistent. And this is when we have what we call dependent equations. The equations depend on each other. They don't leave each other, right? Graphically, they're on top of each other. Not like an intersection at one point where they're independent. Or our third scenario, so if they don't intersect at one point, or they don't intersect at infinite points, if they're not the same graph, then the two lines won't intersect at all. They'll be parallel lines. And parallel lines would mean no solution, right? There'd be no ordered pair that satisfies the two equations. There's no intersection. And that's what we call a inconsistent system. Inconsistent means no solution. And definitely independent equations. So the only time we have dependent equations is with infinite solutions. So let's solve this first system. So here's a system of two linear equations with two variables, x and y. Let's see if we can find an ordered pair, x and y, that satisfies these two equations. Is it one, is it infinite, or is it none? So our first step, is we're going to solve this graphically, is to get it in graphing form. Right? Let's go ahead and get y equal form. So let's go ahead and solve for y. So we'll go ahead and move the x term over. So it'll be y equal to what? Negative 2x plus 5. And let's go ahead and look at equation 2. We'll put it in a different color. Let's go ahead and move the x term over. So we'll go ahead and subtract it over to the other side. And that would give me negative 2y equal to negative 3x plus 4. And then we can divide out our negative 2. Right? And we would have y equal form. So y equal to negative 3 over negative 2, which is 3 halves x. 4 divided by negative 2 is minus 2. So now you could graph your two equations. So you got equation 1, call that y1. And we got equation 2, we'll call that y2. So there are two equations, right, that we want to go graph. And we already know, based off slope-intercept form, the slopes of these two lines are different. So we got a line that decreases with a slope of negative 2, right, down 2, right 1, down 2, right 1, our rise and run. And then we have a line that increases at a slope of 3/2, up 3, right 2, up 3, right 2, which means they're going to intersect. Different slopes, we know intersecting lines. If they're the same slope, different y-intercepts, they would be parallel lines, right? Or if they're the same lines, they'd be, of course, the same graphs, which would be infinite intersection points. So graphically, we know we're going to have a consistent system. They're going to intersect, and we know now they're only going to have one intersection point. So get your calculator out and graph them. And I'm going to pull up my grapher. And here we are on our grapher. So as we look at our calculator here, we've got our two graphs here intersecting at that ordered pair of 2, 1. So I found that intersection point. And you can go to your TI calculator, right? If you're entering in a y1 and y2, your two equations, negative 2x plus 5 and 3/2 x minus 2, you can go to your calc menu and hit the intersect button and lock in on that point of intersection. So yeah, where does it intersect? So we found our solution. So our intersection point is the ordered pair 2, 1. So that implies our solution, right? Our solution set is that ordered pair 2, 1. So we got one solution, right? That's the ordered pair x and y. So x equal 2, y equal 1. Of course, you could check it. You plug it back into the original equations, right? 2 times 2 plus 1, that's 4 plus 1 or 5. 3 times 2 is 6, 3x. So easy 6 minus 2 times y, 2 times 1, 6 minus 2 is 4. So again, you can plug it in and check it too, but we see it with our grapher, right, our solution set. So again, solving it graphically, we can find intersection points if we need to, but we don't have to rely on our grapher, right? We can do it algebraically. So let's move on and look at one of our two algebraic methods. So we've got the substitution method and the elimination method that we're going to talk about. All right, let's take that same example that we just solved graphically. We've had an ordered pair of 2, 1 as a solution. And let's solve it using substitution. Now here's how substitution method works. If you're going to solve algebraically, you've got to get an equation down to one variable, whether that be using substitution or elimination. So to get down to one variable, our first step in the substitution method, step 1, is to pick one of your two equations in your system, since we only got 2 to work with in these examples, and solve for one of the variables. So you got 2 variables to choose from, x or y. And when you do that, you're going to have an expression of x or y, right, for that variable that you can rewrite the other equation with. So let's do that in this example. So I'm going to take this system, and I'm going to go ahead and apply step 1. I'm going to solve. I'll call the top equation equation 1. I'm going to solve it for y, right? Solve for y by subtracting 2x over to the other side of the equation. So we know y equals negative 2x plus 5. Well, here's an expression of x that represents y. So here's where substitution comes in. So we can plug that in to the other equation. So step 2 is our substitution step. Substitute into the other equation, and that will be equation 2. So as we do that, what does equation 2 rewrite as? 3x minus 2 times y minus 2 times negative 2x plus 5 equal to 4, right? And then we can distribute and simplify and solve for x. So we've got an equation with one variable. So minus 2 times negative 2x, that's a positive 4x. Negative 2 times 5 is negative 10, equal to 4. So again, that's our work, right? We used the substitution method. We solved equation 1 for y. We got an expression of x that it represents. And we plugged it into y in the other equation to get that variable with x in it. So that means we're going to find half our solution. We're going to have to find the x value here in a second. So 3x plus 4x is 7x. Minus 10 equal to 4. And as we add 10 on both sides, we get 7x equal to 14. As we divide out the 7, we get x equal to 2. And now we're going to go find y. So once we have x, we're going to find y. And to do that, this is what we call our back substitution step. So we're going to go back up to the beginning. And you can always plug in either of the original equations. Let's go back up to our first step, step 1, define y. So if we know x equal 2, right, we want to know what y equal. So that implies y equals, right, negative 2 times x, negative 2 times 2, plus 5. So negative 4 plus 5, which is 1. So y equal 1. So when x equal 2, y equal 1. So that implies our solution is the ordered pair 2, 1. So remember, this is what we call a consistent system because it has a solution. So if they ask you to describe the system, it can be consistent or inconsistent. Consistent means a solution. And there's only one solution, one intersection point if we were to graph it. These equations are independent of each other. The only time they're dependent is with infinite solutions. So there's a consistent system. So again, we've solved that system algebraically using the substitution method. All right, let's do another one. Let's do one more with substitution method. So here in example B, we've got 2x minus y equal to 1 and 3y equal to 6x minus 3. So as we're solving, now just to be different, I'm going to pick equation 2 this time. So my first step, I'm going to solve equation 2, and you can pick x or y, but definitely easier to solve for y. So let's go ahead and do that. So to solve for y, we can divide out, right, a 3 on both sides. And as we do that, right, we're going to get the equation of y equal, what, 6x over 3, which is 2x minus 1. So y is equal to 2x minus 1. So here's our expression. So we've got an expression of x that we can plug into the other equation. So this is our substitution step. So we're going to plug it back in to the other equation. So step 2, we're going to substitute. Make sure you plug it into the other equation, the one you didn't solve for, which would be our top equation. So that implies 2x minus y will be 2x minus 1 equal 1. So out went y, right? And in went my expression. And as we simplify, now notice what happens on this one. So as we simplify, we need to distribute. So I've got 2x minus 2x plus 1 equal to 1. And the x's eliminate. And I get 1 equal to 1, which is a true statement, but we've eliminated our variable. Well, that means we don't have one value of x. We have infinite solutions. All right? We have infinite ordered pairs that are going to satisfy this system. So if we eliminate our variable altogether out of the system, and we get a true statement. Now, if we get a false statement, something's not true, then we would have no solution. But this is infinite solutions. So as we're writing in our solution set, now, when I say infinite solutions, we're not just saying any ordered pair. So we're talking about all the ordered pairs, x and y, which these two graphs will intersect. Now, based off these infinite solutions, these two graphs should be the same line. So such that y equal, I'm going to put in y equal 2x minus 1, right? That's what our equation's reduced to if you solve for y. So if you look at, for example, let's go back to the beginning, right? If you look at the top equation, we didn't solve that one for y earlier, right? What do we get if we solve that for y? We would subtract the 2x, so we get negative y equal negative 2x plus 1. And then we divide out negative 1 on both sides. And we get y equal to 2x minus 1. So you can see equation 1 and 2, these are the same equations, right? These are the same graphs. So if they're the same graphs, right, we have infinite intersection points, right? Which means we have infinite solutions. And where do they intersect? They intersect on the graph of the line y equal 2x minus 1. So any ordered pair on the graph y equal to x minus 1, right, is an ordered pair on the graph of the other equation, which is y equal to x minus 1. So yeah, our solution set, right, infinite solutions. Now with that said, we have a consistent system. It definitely has a solution. It has infinite solutions. And this is when we call our equations dependent of each other. So these are dependent equations. They don't leave each other. Graphically, they're the same graphs. Right? So that's the substitution method. So let's take a break, and then we'll show you the elimination method.